Hey guys, in this video we are going to finish up section 4.1. We are going to start out here with just talking about arc lengths, and then we're going to start something pretty important. We're not going to do the whole thing, but we are going to start filling out and building a reference sheet that you guys are going to need going forward. So stay tuned, okay? What we're going to start out with here is just calculating arc length, and then we will move into that last little thing where we're going to work on building that little reference sheet. Okay, so arc length. You may remember calculating arc length from geometry. There were two different types of things that you could measure. There was arc length and arc measure. Now, arc measure talked about the corresponding angle measure for that central angle. And that's not exactly what we're doing here. Arc length is talking about whatever, if you were to measure that arc in inches or centimeters or feet or whatever, if you're going to measure it in the measurement of a length, how long is it? Whereas arc measure is usually degrees or radian measure. Okay. So here we're talking about arc length and how can we calculate that. So I'm going to zoom in just a hair because I did draw a little picture to go along with it and see if that helps at all. So what we're dealing with when we're dealing with arc length, you have three things to compare. All right. The arc length is going to be represented with the letter S. That's going to talk about your arc length. But it's going to be very much based off of the angle, that central angle measure, which I marked as theta, and the radius. Okay. The relationship that we actually have is these two different ways, depending on if you're dealing with degrees or if you're dealing with radians. If you're dealing with degrees, we're going to have pi r theta divided by 180 degrees, right? Basically what it does is it's finding a fraction of that circumference, okay? But we're able to divide that. We're able to use that 180 because that's that specific relationship with the pi and the 180 degrees. So pi r theta divided by 180 degrees, that gives you the measure if you are given degrees. But if you're given radians, it's a whole lot more simple. All you have to do to get the arc length is just multiply the radius times that radian measure, theta. Okay, so we're going to go through a problem here. Now, the reason I put a star by the radian one is simply because AP prefers radians, but depending on the problem, you might be forced to use either one. In the example you're seeing for example 3, they actually give us the value as a degree value. So we are going to need to use the top one, even though AP tends to prefer the radians. It doesn't really matter if the problem that you're seeing deals with degrees. So what we have here, they said find the perimeter of a 60-degree slice of pizza with a radius of 7. So let's kind of picture what this looks like. All right, I'm not the best artist, but let's draw a 60-degree angle, something along those lines. And we're supposed to, and now remember, pizzas are typically round, so we're assuming this is round. Now pretend I can draw. Okay, because I can't really. But there's our little pizza. The arc length here would be S, and what we know is that the radius is 7 inches. But no matter where I draw the radius, it's 7. So here is 7, but then also this radius up here is 7. Now you might be tempted to go stick a 7 on this one over here, but it doesn't work like that unless they had told me that this was 1 radian. Okay, if this was 1 radian, then sure, we could do that. But that's not what this is. They said this was 60 degrees. So we're going to have to go based off of our degree measure and solve for the length of this arc. All right, so we're going to use this top equation since they did give me the degree measure. That's the one that says S equals pi r theta divided by 180. And then we just plug the values in. Pi times my radius, which is 7, times theta, which is 60, all divided by 180. Now, I divide things a little weird. You may have noticed that in class. Sometimes my brain looks at these in a weird way. Before I start multiplying it, my brain says, hey, if I'm multiplying by 6d, right, this answer up here is going to have a 0 at the end. This is over 80. It's got a 0 at the end. So if you divide it by 10 on top and bottom, those cancel out. I also see this 6 and this 18. And since all this is multiplied up here, I start canceling right away, right? 6 and 18, 6 goes into itself one time, and it goes into 18 3. So I start reducing before I multiply a lot of times because it saves me some hassle. So really, this is 7 pi over 3 as an exact answer. Now, they want the perimeter of the whole thing, so it will be in my best interest to go ahead and figure out what this is as a decimal. So we'll go to our calculator and we'll type this in. All right, I'm going to clear all that mess out. So what I'm going to do is type in 7 pi divided by 3. And this answer is 7.330, I guess, if we round to 3 decimal places. And what that tells me is that the arc length is 7.33 inches. So to get my perimeter, what we need to do is add up the 3 values. We want the 7 inches plus 7 inches plus 7.33 inches. And that is equal to 21.33 inches. That is our perimeter. Okay? All right, so that was the remainder of our notes there, but we're going to start building something. There will be a later video to go through the entirety of this thing. However, I want to tack this on the end of this lesson just to show you that we can go ahead and start building this thing. And so what we're going to do, and you'll see this should be attached on this page as well so that you can download it and print it out if you need to. We're going to start filling out what's called the unit circle. So you're going to see a paper that has a big fat circle on it, okay, with a whole lot of lines and parentheses and blank spaces, okay. In class, I am providing everybody with an orange paper, an orange copy of this, and throughout the next while, week or so, we're going to start finding moments to add things to this as we learn them. Okay. At this point, we can go ahead and add a few things. So let's start there. We're not going to complete the whole thing, but we are going to start filling in a few values. Okay. Now, I'm also going to go back and reference our notes just a little bit so that I can show you where we've already done some of the calculations that are needed. So you may want to have those notes handy for the 4.1 section. Like I say, we'll reference to them a little bit. What we're going to do is we're going to start filling in some values that are angle measures. Okay, we're going to fill in both degrees and radians for a full circle. Now, what I want you to remember about circles, right? Circles in an entire rotation is 360 degrees or 2 pi, which is what we've been learning here. You look at a half circle, that's 180 degrees or pi radians, right? So what we're going to do here is we're going to talk about what are the radian values, what are the degree values going around the full circle. And the first thing I'm going to do is simply start with quadrant 1, and then we'll go in and add the rest of the quadrants. Okay, now quadrant 1, if you guys don't remember, quadrant 1, if you think of a graph, is this quadrant. That's what we're going to go through and fill in first. We're going to go 0 to 90 degrees and fill in those values. Okay. Okay. So what we're going to do is we're going to assume, because this is how this circle is structured and the whole intention behind it, we're going to assume this is the starting side at all times, your initial side. Okay, so just keep that in mind. This is my starting side at all times. Now, we know that if you have a right angle, that's 90 degrees. Okay, if it's smaller, that's an acute angle, right? We got 30 degrees here. But what if it hasn't opened up at all? If your angle hasn't opened up at all, if that starting side has not gone anywhere to get to the terminal side, then it's fair to say that that is a 0-degree angle. Okay, which I know sounds a little wild, but there at the starting value, that's a 0-degree angle. Okay, well, in radians, coincidentally, that is also 0. So we're going to put those values on here. You see 0 degrees, but that's also coinciding with 0 radians. All right, we're going to zoom in just a hair on here, and then I'll zoom back out as we need to, okay? All right, we're going to fill in a few more. Now, what I want you to remember is that as we go through this, we want to be focusing on what are special angles. So if you think back to your geometry class, you had 2 different special kinds of triangles. You had 30, 60, 90 triangles, and you had 45, 45, 90 triangles. All of those types of angle measures are special angles. Okay, and that's what we're going to reference in this. So this first angle we're going to explore is a 30-degree angle. Okay, the next one, if we're looking at those special angles, right, we had 30, 60, 90, 45, 45, 90. So this one right here is supposed to be the 45 one that we're going to explore. Then we would get to a 60-degree angle, right? This is 60 degrees. And then if we open up to a full-on right angle, that is a 90-degree angle, okay? So just exploring this first little quadrant here, the first 90 degrees, what are these values in radians? Well, as far as these are concerned, we have done several of them. I don't believe we did the 30-degree one, so we're going to do that conversion real quick based off of what we did in our 4.1 lesson, okay? So if you have 30 degrees and we want to convert that to radians, 30 degrees times pi radians over 180 degrees, right? Right? We end up canceling this out. We get 3 pi over 18. This reduces some more. And so we get pi over 6 radians. Okay? So 30 degrees in radian form is actually pi over 6. All right, bear with me. We did do some of these others. I'm going to pull them back in our notes where you should have seen them if you have been here for the notes on those sections. So 45 degrees, we actually did convert that in example 1, part C of the 4.1 notes. So I'm going to pull this back up real quick. 45 degrees, that becomes pi over 4 radians. You can see that math right there, okay? That becomes pi over 4. Now, this is something eventually you're going to memorize, right? For the time being, we're just getting it down and exploring. 60 degrees is also something we've dealt with on example 2. All right, example 2, part A, we were going from radians to degrees. We changed pi over 3 to 60 degrees. Those are equivalent. So 60 degrees, pi over 3, same thing. Okay, so right there, 60 degrees is the same thing as pi over 3 radians. And last but not least for this little part, I want us to look at the 90 degree. That's example 1, part A. Pull that back up right here. It's an awkward angle for me to hold this paper at. All right, this is pi over 2 radians. That's what we got when we did example 1 part A. So this is pi over 2. Now I want to explore this a little bit more, okay? Because it's not just because of converting, right? The conversions are just a nice little algebraic way for us to figure out what these values are, but it's not the only way for you to think through it. So I want us to think about this another way, okay? It might be easier. Honestly, this is usually what my brain thinks about when I work out a unit circle. All right, here we go. Remember how we had said in the section 4.1 when we first started out, 180 degrees is half of a circle. So if I take this all the way out and say 180 degrees is half of a circle, we did a little activity where we took that string and we wrapped it around our circle, and we saw that there were pi radians in half of a circle. Okay, but I want you to think about this. If I take this half of a circle, right, this half of the circle that we have, and you cut that in half, that's pi divided by 2, right? If this whole thing is pi radians, and you cut that in half, that's pi divided by 2. That's another way to remember this is pi over 2, right? Now you think about taking that and cutting it in half, right? If you take pi over 2 and you cut that in half, half of a half is a fourth, which brings us to pi over 4. And that's how that's the same as the 45 degrees. I want you to think about this, guys. What's happened is you're cutting this into equivalent segments or quadrants or sections. What's the word? Equivalent little sectors or sections around your circle, all right? You see this one right here is pi over 6, that's because we have a little pi over 6 section here. But this little section is the same size as taking this half of a circle and dividing it by 6. If you took 180 and divide it by 6, that is 30. So this little section is 1/6 of the top, right? Because 180 degrees divided by 30 is 6. There are 6 of these size sections in the whole top. So this is 1/6 of that top. 1/6 of pi over 6. All right? You can think of a similar idea here. This is pi over 3 because there are 180 divided by 60 is 3. There are 3 sections this size in the top half of that section of that circle. So 3 sections, this is 1/3 of this top section. Another third, another third. So you can keep adding those on to get all the way to pi. There are many people who just identify things or just focus on it as pieces like that so that they don't have to do all of the unit conversions all the time. You get really comfortable with being able to find the special ones at the very least by memorizing them because they get used so frequently. We're going to go through, fill out the rest of this top section of the circle, and then we may go down to the bottom section. So what I want us to think about is if we keep going and we use those special little angles, okay, this is another 30 degrees. So from 90, another 30 degrees, that's going to land us at 120 degrees. Okay, these are still going to have like the same kind of little increments. So whereas these were 15 degrees apart, these are going to also be 15 degrees apart. This will be 135, another 15 degrees, 150, and then we go from 150 to 180. Okay, but look, this is the beauty. Degrees start getting really, really cumbersome. But I want you to look at the cool thing that happens with your radians. All right. Remember how we said that we have our little sections like this? Let's look at the 1/4 first, okay? Right? We had half of a half was 1/4. okay? I want you to count these sections. We have 1/4 section right here, plus another one, so that's 2/4, or yeah, 2/4, 3/4. This one right here, 3 pi over 4, 3/4, right? 3/4 of the way around that top section. Look at your little 1/6 sections. We have 1, 2/6, 3/6, 4/6. Now I want to talk about 4/6 for just a moment, because 4/6 can actually be represented in a reduced way. So we'll come back to that in a moment. 4/6, 5/6 cannot be reduced. 5 pi over 6. Okay, go back to 4/6 for just a moment. Okay, 4 pi over 6 actually reduces because 2 goes into both of those and becomes 2 pi over 3. And then look at this, guys. It's so cool. It's so cool. I love the patterns. You see this pi over 3? 2 pi over 3. This pi over 4, 3 pi over 4. We have pi over 6, 5 pi over 6. I just love the patterns that come out of that. Okay, let's keep going. We're going to go around the bottom. Okay. All right, let's finish out doing the degrees along the whole lower part of our circle. So 180 degrees, but now we're going to add on 30. So this is 10 or 210. Then we go another 15. So this is 225. 15, this is 240. Then another 30. This is going to be 270 degrees down at the bottom. Okay. Keep going. We're going to add another 30. This is 300 degrees. 15 degrees here. We're going to add 315. This is 330, 360. Okay. So again, we're just going in those same little increments all the way around. And the reason is because we're able to end up using those angles, those special angles, to calculate values with them. And it's really, really neat how this all comes together in the end. All right, last thing we're going to do is go through and get these values for our pi's. Now remember that the whole top section was 1 pi. But then when we add on the bottom section, we get 1 pi plus another pi makes a total of 2 pi for that full rotation in radian form. Okay, but what about these others? What are we going to do with these other things? Well, first things first, okay? All right, we need to figure out what this one is, right? The halfway point between these two. Think of halfway between 1 and 2. Right? Halfway between 1 and 2 is 1.5 or 3 halves. This is 3 pi over 2. Now, again, you can do the calculations we actually have before. I want you to look at this. 270 degrees in radian form. We did this in, I believe, yeah, we did this in example 2 already. I tried to pick special angles when I did these examples. So 3 pi over 2 is 270 degrees. We did that conversion already. So if you don't believe me by looking at the picture, look at the conversions that we've done. 270 degrees, 3 pi over 2. Okay, we've also done some of these other ones, but I want us to look at the patterns on here and see if we can figure out what's going on and if we can get these a little bit easier. Okay, so I want us to let's look at the 1/4 ones. That's the guys that are exactly in the middle between these quadrants. That would be this one and then this 315. Those ones are 1/4 of the way around the top or around the bottom. Okay, so remember this was 1/4, 2/4, 3/4, 4/4, and it gets you to a full pi. But then the next one, if that was 4/4, this one here is 5/4. So 5 pi over 4. This one would be 6/4, but it reduces to 3 halves. Okay, 6/4, 7/4. So 7 pi over 4. All right, let's look at our 1/6 type of pattern. Remember, this was 1/6, 2/6, which reduces to 1/3, 3/6 reduces to pi over 2, 3/6, 4/6, 5/6, 6/6, which brings us to a pi, a whole pi. That was 6/6. This is 7/6 around. So that is 7 pi over 6. This guy down here would be 8/6. But remember that this is going to reduce and actually become 4 pi over 3. All right. That was 6/6. That was 8/6, 9/6, 10/6, which we can also deal with. 10 pi over 6 would reduce and become 5 pi over 3. And then over here, our last one, that was 10/6. This is 11/6. 11 pi over 6. Okay, so you're going to see some really cool patterns emerging in here. You see how these both have a denominator of 6. These both have 4 on the bottom. These both have 3 on the bottom, right? All of the ones that, like the 90 and that 270, they have a 2 on the bottom, right? So you're going to see these really cool patterns that emerge in here. You're going to see more as we start building this thing. Our unit circle is a huge, huge idea, and we'll actually be doing a test that is legitimately just the unit circle. And can you fill in the values? So at this point, we've actually covered enough stuff to be able to do about half of it. However, we haven't talked about how to get the rest of these values, and that's what we'll be doing in some of our future lessons so that we can fill in those values too. Okay, like I say, in class, you'll be getting a yellow copy that we will fill in, not yellow, orange, that you will fill in class as we can. And you don't want to lose that because it's kind of your reference sheet to allow you to study and practice and get more solid with knowing these values. Okay. Anyways, that is it for this lesson. I know that was a little bit long, but I think it was important that we went ahead and start filling in that unit circle because it just will make our lives easier in the long run. All right? All right, guys, good luck, and I will see you in the next one. Bye!